Hi and welcome back. So let's take a look at these rich comparisons. That's actually quite straightforward. And as I mentioned in the lecture, if the comparison doesn't exist, then Python will try to reverse the operands and the operator, right? So unlike the arithmetic operators, this doesn't require both operands to be of the same type. So let's take a look at this in some detail. It's straightforward, but we need to pay attention to some of the details. So let's go ahead and do our init. I'm going to create a simple 2D vector, so it will expect two arguments. So I'm going to store x in self.x and self.y will take y, so just bare attributes. I'm also going to write a quick representation, self, and then here I'm going to return the formatted string. It'll be a vector, and it's going to have two components, x equals and y equals. And then I'm going to interpolate self.x and self.y in our representation. Okay, so now we have v1 equals vector 0, 0. Let's do another vector, v2, which is also vector 0, 0. And let's go ahead and print the ID of v1 and print the ID of v2. Now, as expected, these are not the same objects, right? They're different objects, different memory addresses. So when we do v1 equals v2, we get false because essentially we haven't implemented a dunder equal method. So Python defaults to using the is essentially between the two objects. So it's actually comparing the memory addresses. Since they're not equal, these two objects are not considered equal. So let's go ahead and implement the equal method. So let me copy paste this code and let's implement the equals method. So def dunder eq self comma other, and here I'm going to say if is instance other comma vector. So I do want both of my objects to be, both of my operands basically, to be vectors. And if that's the case, then I'm going to return self.x equals other.x and self.y equals other.y. So I'm going to do value comparisons between the x and y components. If that's not the case, then I'm going to return a not implemented. So now we can go ahead and create some vectors. So let's create vector 1, 1, and let's create vector 2, vector 1, 1 as well. So they should be now equal vectors. And then let's do a third one that's going to be different. We'll have different components, let's say 10 and 10. So now you'll see that v1 equals v2 and v1 is v2. You'll see that v1 is indeed equal to v2, but it is not v2. And then with v1 equals v3, obviously that will be false as well. Now, we can even support equality comparisons with other iterable types. Let's say that I want to support the equality comparison between a vector and a tuple. Let's go ahead and take this code again. So I'm going to copy and paste it. And I'm going to now modify this equality a little bit. I'm going to say if is instance self or other comma tuple. So I'm going to allow comparisons to tuples. Now I would technically have to go ahead and check, is it the correct number of dimensions? I should have two items in the tuple and so on. I'm not going to do this. Instead, what I'm going to do is I'm going to create a new vector and I'm going to pass in the unpacked other. So I'm going to unpack other. If it has, not exactly two elements in that, it's going to raise an exception because we won't be able to call the init method properly when we create this vector. So we'll get an exception. So I'm going to leave it at that and use it that way. Now that I have other as a vector, now I can check saying, okay, well, if other is a vector, either it was a vector or it got transformed to a vector and it did that okay, then go ahead and use what we had before, otherwise return not implemented. And we could write this in different ways. We could also, handle lists, maybe iterables in general, things like that. I just want to keep it simple. So let's go ahead and create a new vector, 10, 11, let's say. And I want to check if v1 is equal to 10, 11, right? So what is this going to add? It's going to call the dunder eq method. Let's actually go ahead and put in a print statement just so we can see that it was called. So now when I run this equality, eq was called and of course it returned true because it did this transformation to a vector and then it tested the components. What's interesting is that if I do 10, 11 equal to v1, now it's actually going to call the equality method of the tuple, passing it v1, passing it the vector. Now the tuple class in Python doesn't know how to handle our custom vector class, so it's going to return not implemented. Python then in turn is going to flip this equality around and say, okay, well, if I can test it this way, can I test it the other way? Can I reflect this and say v1 equals 10 and 11? So in fact, as you can see, our equals method was still called because Python reflected this comparison operator, and so we get true as well. Now we can implement the other rich comparison operators in the same way. Let's go ahead and implement the less than operator. So for less than, I'm going to consider a vector to be less than another vector if its absolute value is less than the absolute value of the other operator, or the other operand. So basically I'm going to use the Euclidean norm of the vector, or the distance from the origin, if you want to think of your two-dimensional vector as a point. So let's go ahead and do that. So I'm going to copy paste this code down here, and let's go ahead and import the square root function from the math module. So from math, import square root, because we're going to need that. And let's implement the less than method. So def less than, and then self other. Okay. So if I'm going to do the same trick here, I'm going to allow comparing to a tuple. So I'm going to say if his instance other, comma tuple, then I'm going to make other equal to the vector of the unpacked tuple. So I'm going to unpack other into individual arguments, into positional arguments, pass that to a vector, and create a new vector. Now I can check if my other is an instance of vector, then I'm going to return the absolute value of self less than the absolute value of other. That's how I'm going to do that. Now, of course, I don't have anything for the absolute value on this class yet, so I need to define it. So I'm going to define absolute method of self, and that's going to return the square root of self.x squared plus self.y squared, like so. Okay? So now we can use this class and we can use the less than operator. Let's try it. Vector 0, 0, and let's do vector 2 equal to vector 1, 1. So now we get that v2 is less than v1. That is false, right? And v1 is less than v2 is true. So that works fine. Now what's interesting is that the greater than operator will work. If I do v2 greater than v1, what happens is that I don't have a dunder GT method defined on my class. So Python is going to flip this around and say, okay, well, if that's not implemented, can I look at v1 less than v2? And so it's still going to call the less than. In fact, let's put in a print statement to see that. So when we do that, obviously LT was called here as well. And now when I do the greater than, you'll see that LT was called as well. But of course, it reversed the operation. So the other was v2, right, in here, and self was v1. It just said v1 dot under LT v2. So what about with tuples? Can we do that? Can we say v1 is less than the tuple 1, 1? Well, we actually wrote code to handle that. So we have the dunder less than was called, and we get true. Now, what about the other way around? Can we say 1, 1 is greater than v1? And that works. And again, it called this. Again, tuple doesn't have or can't handle v1 as an operand for its greater than operator. So Python reverses the comparison. It reflects it. And instead, it's going to try v1 less than 1, 1. And of course, we've implemented that functionality. So now you might be thinking, okay, well, this class now has a less than defined and it has equality defined. So can it support something like v1 less than or equal to v2, right? And the answer is no, it's not supported directly. So we would have to implement this ourselves. So let's go ahead and do that. So I'm going to copy this code and I'm going to paste it down here. And then here, I'm going to define the less than or equal to self and other. So here, what I'm going to do is I'm not going to repeat all the code that I have. I'm just going to return self equals other or self less than other. So now we can try this again. Let's say v1 equals vector 0, 0. And we can say, let's do vector v2 is also vector 0, 0. And let's do vector v3, which is going to be 1, 1. And now we can test things like v1 is less than or equal to v2. That works. As you can see, it did call the equality. Why did it not call the less than, right? Why did it not call the less than operation method? Well, because this is a short-circuited Boolean expression. So it tried self equals other. The answer was true. So it didn't have to evaluate this second part over here. It just returned, right, the result of this, which was true. Of course, if we did this with something else, like v1 is less than or equal to v3, in that case, they're not equal. So this didn't resolve the Boolean expression here. So now it had to look at this one, and this is why LT was called. So we have less than or equal to. What about greater than or equal to? Could we say v1 greater than or equal to v3? And the answer is yes, that works. It basically calls EQ and then LT. So we don't have a greater than or equal to defined, right? We don't have the dunder-GE method defined in our class. So Python just flipped it around and said, okay, well, do you have v3 with a less than or equal to v1? And of course we do. So it was able to run the calculation. Now we also get for free the not equals. So v1 not equal to v2 will be false. How did it do this? Essentially by saying not v1 equals v2. We didn't have the not equal operator defined. We didn't have the dunder-NE method defined in our class. So it was able to derive it by using this instead. Now in many cases, we can derive most of the rich comparison operators from just two base ones. The equals method, definitely, and one other one, maybe the less than or the less than or equal to. And what I mean by this is this. Let me go ahead and just paste something from the Jupyter Notebook that you can download. And let me put that in here. So if you have, let's say, the equals and the less than defined on the class, then less than or equal to is simply this. A equals B or A is less than B. A greater than B is the same as saying B less than A. A greater than or equal to B is the same as saying A equals B or B is less than A. And A not equal to B is the same as saying not A equals B. And then you have something similar if, let's say, your class defines the equals and the underscore, the dunder LT. Then, A less than B is A less than or equal to B and not A equals B, and so on. So it's possible very often to derive basically the rich comparison operators just from two base ones, either the equals and less than, or the equals and the less than or equal to, or the equals and the greater than, and so on. So in fact, you can use a special decorator that's available in Python, and I have covered this in other parts of this series, but it is called the total ordering decorator, and it comes from the functools module. And basically, it's something that allows you to specify or to add total ordering on your class, basically by implementing only two methods, the equals method and one of the rich comparison operators. And this total ordering decorator will fill in the gaps for us. So we don't have to go ahead and write, at the very least here, we had to write the equals, the less than, and then the less than or equal to, and then everything else followed. Here we can get by with even less by using total ordering. So let's go ahead and do just a quick sample. So let's do an init, and then we'll just pass x and self and x, and then self.x will be x. So basically this is just a number wrapper class. So it doesn't really do anything useful, but it serves to illustrate the purpose here. So I'm going to print out that EQ was called, and then if, well, let me fix this typo, if is instance other comma number, then I'm going to return self.x equals other.x. So I'm specifying the equality here. Otherwise, I'm going to return not implemented. Then I'm also going to define the less than function. So the less than method, to be more exact. So self and other. And again, I'm just going to print out LT was called. And if is instance other number, then I'm going to just check whether the numbers are less than or equal to. So return self.x less than other.x, like so. Otherwise, I'm going to return not implemented, like so. Okay, so very straightforward, very simple implementation. So let's do a equals number 1, b equals number 2, and c equals number 1 again. So we should have a equal to c, so number. So now you can see a is less than b is true because the less than was called. Now a less than or equal to b is also true, and the less than was called, right? Because 1 is less than 2. Now if I tried a less than or equal to c, you'll notice that the less than was called and the equals was called, right? Because it has to test both less than, and a is not less than c, so now it has to test the equality, and so that worked. And then we have a is greater than or equal to b, that's implemented. A is greater than b is implemented as well. A is not equal to b. Okay, all these are implemented by the total ordering decorator. Now, there is one thing that I want to point out. The documentation for the total ordering decorator specifies that you technically don't need to implement the dunder equals method. Only, let's say, the dunder LT would be sufficient. Now, technically that's true, but in many cases it's not what we want. Why? Well, technically the dunder equal method doesn't have to be implemented in our class because our class already has it by default, as we saw earlier. But what is the default? It's identity. So if I don't have this over here, we kind of get some weird behavior. Let me show you if we don't define the equals, and let's define those 3 numbers over here. And let's see what we get for the results. So first of all, is a equal to c? And the answer is false because they're not the same objects, right? Now it's using identity. Well, what about a less than or equal to c? Well, that's going to be false as well. So we get some kind of weird behavior here. So this is why, in fact, if you're going to use the total ordering, you probably want to implement the dunder equals method, even though the documentation says you don't have to. If you want to get consistent behavior the way you would expect it, you're going to need to implement it as well. All right, so thanks for watching, and I'll see you in the next video.